There are three types of exposing systems. First, a contact printing. The contact printings are methods that wafer and masks are sticked together by using vacuum, so that it can has good image resolutions. However, it uses a mask that same size with a wafers. So, and there can be a this method can damage to mask and wafers. And there is a proximity printing. Proximity printing is a having a space between a wafer and mask, so it has lower resolutions that contact printing. However, it also it can be get less damage than the contact printing. However, it has a poor resolutions. Lastly, there is a projection printing. Projection printing is a projecting the image to the wafer, so that using a condensing lens. So the mask doesn't need it to be same size with the wafer. However, it uses a optical systems, so it is very expensive. Optical systems are complicated. In projection printing, we use a steppers. We use steppers because the mask is not same size with the wafers. So we use it, we exposures these patterns using a optical systems to zoom in. So to exposure to each die, we exposure in wafers in one shot on one die. So after we print the pattern of one die, we should move to next one. However, this method has a misalignment issues. So nowadays, we use a scanner method. The scanner method is that the reticles and the wafers move the opposite way, like a convolution sum, so that it can be more aligned. The reason why using scanners in the optical systems in the lens, the side of the lens can be distorted, so we don't use this part, and we use only a center side of the lens, so prevent these distortions at edge of the die. And there is a numerical aperture and depth of focus. As the numerical apertures get smaller, then the depth of focus will be get higher. And using the numerical apertures and depth of focus are important. If the numerical aperture is lower, then the depth of focus would be get high. However, the intensity of light can be get smaller. So the advantage that having more density of focus, that can be we can exposure the photoresist more sharply, not relevant to this discontinuous. So having more density, depth of focus is very important. So there is another concept, the critical distance. The critical distance are anti-proportional to the numerical apertures and proportional to the light's wavelengths. So we call this relationship as LELE's equations. The meaning of critical distance is that uh, how finely we can make the patterns. So, and there is another technique, the immersion lithography. Uh, the immersion lithography is used in to maximize the critical distance using this reflect the difference between reflective index. So by using more reflective index to shorten the critical distance, by shortening critical distance, we can make more fine, more small scale patterns. And we measure this critical distance using electron microscope. Using microscope, we can measure the difference, the slope between the edge and the distance between the lines. When we print the selective patterns in the wafers, we use light source like ultraviolet, and nowadays we normally use a argon fluorescent UV light, which has 193 nanometer wavelengths. This argon ARF light has a limit, so to for micro scale patterns, nowadays we use extreme ultra violet light. The using a shorter wavelength light has effective uh, effective methods to engraving the microscale patterns. The EUV, the extreme ultraviolet lithography, uses a thin molecules, liquidized molecules. So if we expose to the CO2 high energy lasers to thin, then the plasma, the thin plasma exerts the light. The certain light, the 13 nanometer wavelengths, the lasers, in extreme ultraviolet light or lasers, we don't use these commonly used projection, printing, or something else. The three types. In EUV, we use these reticles here. We use this reflection by uses reflections to expose to the wafers. In these systems, EUV systems, they're very complicated optical systems, and making these EUVs is very hard using a vacuum systems. And also there is another problem. The pellicles has a pellicles work as another mediums to the light propagation course. So there are two diffractions, of course, in the total projectile. So it can affect to the resolutions of printing. And there is a photoresist. A photoresist is a mask for the wafers. It can work as two types. First of all, a positive resist and negative resist. In positive resist, uh, the exposed area to the light makes weakens the chain on the photoresist. So, and after they develop, uh, the certain patterns, exposed patterns are disappeared. In the negative resist, uh, on the other hand, it strengthens the chain so that uh, after develop, it removes on another area as it removes area that is not exposed to the mask. There is very uh, important factors in the photoresist. The threshold energies are means that the minimum energies to activate the photoresist. It is important to getting these parameters because uh, we would like to exposures energy to the more than the threshold energy, and we coat the wafers before we expose to the light. We coat the photoresist on the wafer surface. First of all, there is a spin coating method. The spin coating method can be defined as four types, four procedures. First, we dispense the photoresist liquid in the wafer surface, and then we accelerate the spin the wafers to deposit evenly, and after that, by equip using a equally uh, velocity, so make it more evenly disposed, and after that we soft bake to remove this uh, liquid liquid uh, liquid component like solvent, and using having a spin coating, there is a very important four factors. First of all, the viscosity. The viscosity is as PR has lower viscosity, then it would be easier to uh, dispose dispose to the wafers, and after that, the accelerations is also important, and the spin speed and the spin time is very important to the thickness of the photoresist. And there are defects that not using correct correct or spin times, accelerations, or spin speed. it can be there can be on particles for the bubbles. It can be too fast that can be not deposited too evenly. For the large wafers, we use a deep coatings, which dips into the wafer on photoresist. In these matters, it is important by pulling speed and pulling time, and there is a spray coatings using a very finite molecules to depose evenly. And there is a classification for defects. First of all, the non-killer defects, which are not effects to the wire line, and there is a potential latent reliability defect, which is that it is not critical than the killer defect, but it can be source of defect for further process. And the killer defect, for the killer defect, we cannot fix the die, so we cannot use this die for the killer defect. The killer defect makes the blocks the metal wires or lines, and it can also be short to two lines. So the defects are caused by almost the particles. So the cleaning the wafers is very important process. First of all, we clean these organic materials using acid. Second, we remove this thin layer of silicon dioxide, which are made by nature, and then we remove the heavy metal or ionic substance using hydraulic fluorous acid. There is a problems on photoresist. Then if we using light, then the YT Bragg's law, as the silicon wafers are very highly reflective, so they can be reflected on the PRs, and after then it can be reflected on the silicon wafers. So there is there is difference between path lengths. So if the difference is the multiple of half of the wavelengths, then the destructive interference can be occurred. And if the multiples of the wavelengths, then the constructive interference can occur. So it makes the PRs
네,
makes photoresist not activated. The photoresist can be were not activated, so can be affect to the resolutions. So to prevent the interference, we use ARC, anti-reflections coatings. So using the materials like cyan, silicon oxide nitrate to absorb the reflected light, or by using the reflective index to prevent the second reflection on the substrate. There is a top ARC and bottom ARC. We can put it on top of the photoresist or the bottom of the photoresist. Nowadays, we don't use a top ARCs. The top ARC and bottom ARC can be used with the polymers, but it has defect because the photoresists are also polymers, so that they can be solutes that can be soluted with each other, and also it can be not used as hard mask. Nowadays we use these bottom ARC or bark using inorganic materials like cyan. The mechanism is that using the difference of reflective index, so that they cause destructive interference to prevent the second reflections. So there is another knob for solving these problems, the PSM. The PSM, the phase shift mask, is also solving the problems due to constructive interference. So we cannot shape these micro scale patterns. We use this 180 degrees phase shift materials in the neighboring mask, so we can make more higher resolutions on the patterns. And there is a we call this method using these phase shift materials, the attenuated phase shift mask. And there is another technique called alternating phase shift mask, is that we improvise using this difference of distance, so that we can make difference destructive interference. So there is a OPC, optical proximity corrections. There is limitations using PSM or ARCs. Is that using this like patterns in here, they can be more exposed in the there can be more exposed areas and less exposed areas. So we compute these diffractions or interference patterns so that we can use computers to calculate the exact patterns needed for mask, for calculate the mask for needed exact patterns, making the exact patterns. And lastly, there is OAI, off-axis illuminations. The OAI is the reason why we use the OAI is that similar to the Fourier series, as degree of Fourier series goes higher, then we can restore the original signals very close to the original signals. So using this method, by alternating the light source degrees, optical degrees, so that it can make more exact patterns, more higher resolution patterns. So we use this off-axis illumination. Also, uh, there is advantage that using higher diffracted uh, light wave, so we can get more higher resolutions. Also, there is a deeper the distance of focus, not shortening the numerical apertures. So it can be more. It can get more light intensity, not shortening the numerical apertures. Also, it can make more depth of focus. Nowadays, using to use these off-axis illuminations, so we use the not dipole or quadrupole apertures. Using these quadrupole apertures are more effective to the shaping the microscale line or space patterns, and the annular apertures is less resolutions than quadrupole apertures, but it is more independent oriented. Techniques like ARCs or PSM, OPCs are alternating this distance difference of path distance, so it prevents to diffractions or interference problems. However, for the more microscale patterns, we use LELE or as self-aligned double patterning. The LELE is meaning for that litho edge. So there is two approach using LELE. First of all, the double trench approach. In double trench, like we shape like a gear, which uses hard mask and photoresist. So first of all, we print a trench. After that, between the trench, we make the another trench between them, so we can shape more fine patterns than the just exposing them once. And there is a line approach, double line approach, is that after we make smaller patterns, smallest pattern as possible, then the after that, in between them, we make another patterns in them. After that, we etch so that we can make more microscale patterns between them. But however, there is problems using a LELE. First of all, there is we use litho process twice, so there is a misalignment issues. The misalignment issues leads to the overlay problems. The overlay problem is that the line are not evenly distanted, but one is long and short, long and short. the distance between the fins or the lines makes the issues in capacitance. In FinFET, we use a multi-fin to give more current or to give more current, so for the better swing. So there is a capacitance between the area between the fins. These capacitance are uh, connected parallels equivalently if we use multi-fin structures. So this uh, difference of the length between the fins makes the more capacitance, very high capacitance, so it can be affected to device performance. And there is another problem is that if we not it bends, the fins are bented, so it causes more capacitance, so it affects to the device performance. And there is a self-aligned double patterning. The self-aligned double, the meaning of self-aligned is that we use this spacer. So first of all, read this. We litho the minimum patterns as possible, and we etch this bark and sacrificial hard mask. After that, we deposit the CVDs or deposit the spacers, and then we remove the sacrificial hard mask, and then we etch through these wafers, so make these similar microscale patterns like fins. The process can be overlapped. So if we deposit spacers again using the spacer as sacrificial hard mask, so then we can make more microscale patterns. However, it has problems that if we when we first photoresist the litho the sacrificial hard mask, the critical distance is not smaller than the exposures. So when there is a there continuity problem, and if we etching the sacrificial hard mask, then there is problem. It etches also the spacers, so there is issues on the further process, or it can cause similar to the overlay problems, and the distance between the fins can be not evenly distanced.